Hi, everyone. So I'm Noah, and I'm here to present you a project that I did after completing a deep learning course given by the Machine and Deep Learning Israel community. This project was together with Nexal, and it dealt with detecting obstacles on the road. So before I start, I want to say that I did this entire project together with Checha. If you have any questions, she's back there sitting. So what was our project about? Advanced driver assistance systems. One of their main functions is to alert the drivers when there are some obstacles that the car might run into. So basically, we need to know where they are and alert the driver. And if we look at the common ways to do this, for example, if we have semantic segmentation on the left, where every pixel in the image needs to be classified, whether it's a car, a pedestrian, the road, etc., or the object detection, when we need to actually detect all the objects in the image. For example, you could look at the car over here that's very far away, and it's not actually posing any danger because we have a car that's closer to us. And both of those common practices are very heavy computationally and requires a lot of time. And while driving, we needed to perform in real time. So in 2015, a work called StixelNet was published. The innovation in this work is that instead of looking at the entire picture, now we're looking at the stixel, basically this narrow column of a part of the image. And in this stixel, what the network needs to provide us is the location where the first obstacle begins. Mainly, we're just dividing the stixel into bins, and the network outputs the bin where the obstacle begins. You can see here marked in red. So the goal of our project was to implement a faster version of StixelNet. And why is that? Because the original architecture had 2 convolution layers and then 3 fully connected layers. And the fully connected layers requires a lot of parameters, and they take a lot of computational time. So what we did was implement 2 architectures, the MobileNet v1 and the MobileNet v2. Both of those architectures are very fast. They're fully convolutional. They're known to be a light version and still get good results. In this project, we use the Kitty database. It's a publicly available database. Basically, it's a database of car driving around, and there is images from the driving, there is depth information, and it's all available. So for the depth information, Dan Levy, the author of the StixelNet paper, he published the ground truth results that were extracted automatically. And after finishing the pre-processing, we had about 1 million stixels, and about a third of them had the ground truth data. So now let's talk a little bit about the metrics to see how we can evaluate the performances of the networks. So as you recall, I said that we're dividing each stixel into bins, and then we want to know if the network classify the stixels where the obstacle starts. If it does fall on the same bin, then we say it's correct, and if it misses, so it doesn't, we don't count it. And then we want to know the percentage of stixels that were accurately classified, and we call it the top 1 accuracy. We have another metric, and this metric here is the graph. I'll start. So in the bottom, we have the number of pixels that we allow the obstacle to begin in. And then on the y-action, we have the percentage or the fraction of the results that were classified correctly within this range of error. So if we look at an error of 10 pixels, in this example, we have about 85% of the stixels that were classified correctly. And we're interested in the area under curve of this graph. So let's look at a little bit of the results. On the first line, we have the StixelNet, which is the architecture that I told you before was published in the paper. And here we have 2.5 architectures that we implemented, the MobileNet v1, the MobileNet v2, and the MobileNet v2 with a asymmetric kernels. Basically, it was in a rectangular shape because the stixels are very elongated. And in the original paper, they also used asymmetric kernels. So we wanted to see if it will improve our results. We found out that it didn't, but we tried it anyway. So if we look to compare between those networks, in the StixelNet we had more than 20 million parameters, which is quite a lot. And in the mobile net, we got it about an order of magnitude less. We had less than 5 million parameters for the V1 and less than 2 million for the V2. If we look at the top one accuracy, the StixelNet does perform better, but by about 10%, even 9% actually. And when we're looking at the AUC, we can see that the results are very, very similar. We basically got the same performance. If we look at it as a graph, so on the right you see the graph from the paper. We're comparing to the soft max loss because it's a classification problem. And on the left you can see our results. In all of them, the area under curve is about 0.84 or 85 or 86 in the StixelNet paper. We were very satisfied with those results. And also it's interesting to look at the images to see how actually the network performed. So on the bottom you see the ground truth, and on the top you see our prediction. And so first of all, we can see that the results are satisfying. And also I think it's very interesting to look where the network actually missed and misclassified some things. So if we look at the fence, we see that there is a lot of noise there in where the obstacle begins. And it can be due to several reasons. For example, if there are not a lot of fences in the dataset is not that big. And also there is a rapid change of the colors and many edges, which also is hard for our network. And if we're talking about edges, you can see that in the shadow of the car, it also misclassified the shadow as a beginning of an obstacle, which is again talking about a sharp edge of the colors. But also something that I found really interesting is if we look at the red sign on the left of the right image, we can see on the bottom that it actually, the automatic ground truth didn't classify it completely correctly. We can see that the legs are classified correctly on the top image, what our algorithm has output. Well, actually it counted as a miss in our metrics, but it's the better result. So I just want to share a few things that we learned along the way, and it was our first project, and we did some rookie mistakes, we can call it, that people should avoid or at least learn from other people's experience. So first of all, real life data is dirty, it's unbalanced, you need to work really hard to clean it, and you shouldn't forget that. And also, it's really good to achieve convergence on a small data set and make sure it is balanced, because otherwise you didn't get actually anything. What else we did was building a pipeline with the dataset API and the estimator API. Those APIs didn't have a lot of documentation while we were working on them. So we had to be creative when we were searching for solutions. And one of the stories I really like is that Shachar actually found a solution to one problem in a comment of a YouTube tutorial. Yeah, true story. So also we saw in the results that the mobile architectures showed similar results, and we had about 10% of the parameters. And also check the predicted values and the network certainty along the way. It's really important to see that your network actually learned something and you're not just looking at noise that's performing for some reason a little bit better than random. And also I wanted to share 2 really good resources containing many advice on how to train your neural networks and avoid common mistakes. And that's it. Thank you very much. Questions?
You talked about the task as a classification task, and therefore the evaluation metrics were all kinds of accuracy metrics. But in fact, in real life, it's matter whether the mistakes was far away or like quite close to the real obstacle, right? You can think about all kinds of like distance metrics. Did you try some of them, or there is something about it?
So it was in our future plans to work on other metrics that, well, I'll go to the metric slide, that talk about the distance, but also the area under curve does get you some information about how far away we are from the correct classification. And also in the paper itself, we didn't do it because they got really similar results, but they also looked at it as a regression problem. They tried a lot of things, and we started with classification because we thought it would be faster and will still give us interesting results. So the question was, how long did it take us? And I think we worked about it for about 2 months, about 2-3 days a week, I think. Yeah, Shachar seems to agree with me. Yeah, so it was a lot of, we were both working like part-time jobs, and we invested a few days and many evenings, I think. Okay, thank you very much.
Hi everyone, I'm Yonatan Hadar from Yellow, and I'm going to talk about one of the scariest things in data science, data leakage. So what is data leakage? According to Kaggle, data leakage is the creation of unexpected additional information in the training data, allowing the model to make unrealistically good predictions. Or, in a simpler version, just anything that will make your research performance be better than your production performance. So, in this talk, I'm going to demonstrate some best practices to how to avoid, how to discover, and how to investigate data leakage with 2 examples. My first example is about a loan default prediction model. So we had data about loans to small businesses, and we're trying to predict if the loan is a good loan like this one, where all of the payments is returned on time, or a bad loan like this one, that one of the payment was late, a default loan. So I ran my first machine learning model and got this ROC. At first I said, whoa, this is an amazing result. And after a second of pure happiness, I said, yeah, I have a data leakage. Again. So, okay, the easiest way to discover data leakage is just to say that the model performance is too good to be true. Here it was definitely the case. So what one can you do? The first thing I did was looking for bugs, like entering the label as a feature to the model. This wasn't the case here, so I started digging into the model. Feature importance is a very good way to discover leakage. Here we can see that the number of payments is a very strong feature in the model. This made me suspicious due to 2 reasons. First of all, according to my domain knowledge, this shouldn't be such a strong feature. And second, feature importance distribution is usually more logarithmic shape and not one very strong feature like here. So now we have another indication for a leakage, and we know on what feature to focus. Another good practice is looking at interpretable models like decision trees or linear models. Here we can see that at the root of the tree, we had about 60% bad loans, and after the first split in the red, we have almost 85%. This is a very good split that doesn't really make sense. So this is probably a leakage. So what was the leakage? We had data from only 18 months, so we had a problem with the long-term loans. We had loans like this one that ended inside a data set, so obviously we could use them. We had loans like this one that so far were good loans, but we don't know what will happen next, so we can't use them. And we had loans like this one that didn't end yet, but we already know that one payment was late. So this is the default loan, and we used it for the model. This created a bias that in the long loans group, we have almost only a default label, which is not how the reality works. So we fixed this bias by including only loans that their planned end date has already passed. My second example is from the medical field. We had data about patients that had wearable devices on them, and we were trying to predict if a patient will have an abnormal event or an attack of his disease using the wearable data. Here in the plot, we can see the activity of a patient at night, and in red, we can see the activity during an attack. So I ran my model and got this ROC. This is not such a good ROC like the first one, but it has a perfect part in its beginning. Straight or almost straight lines in the ROC are usually an indication for a leakage that the model is exploiting. So I started investigating the model. This time I did it with Lime. Lime is a very cool Python package that explains specific prediction of black box models. I took the examples with the highest probability from the model and started looking at them with Lime. I saw that the explanation of sleep time between 7.5 and 9.5 hours has returned in most of them. This made me suspicious because this didn't really connect it to my domain knowledge. So after investigating this explanation a little bit more, I found that it almost isolates completely only one patient. So in dataset that had groups in them, like this one, we can't use a normal random cross-validation, and we need to use group cross-validation, where we train on several patients and test on other. This way we can make sure that our model will generalize to new patients when it will go to production. Here we can see every ROC is the ROC of one fold in a four-fold group cross-validation, containing different patients every time. We can see that 3 out of the 4 folds are almost completely random, and only one fold performs well. So we have here a group leakage. So what was the leakage? We had a few patients with a very large attack percent, and this made the model learn how to predict if a patient is a good patient or a bad patient and not the actual patterns of an attack. We fixed it by making it harder for the model to distinguish between patients by normalizing the features per patient and evaluating with group cross-validation. So we had the too good to be true method, the perfect part in the ROC, the problematic feature importance, the high variance in cross-validation, and inspecting interpretable models. So here are some tips to avoid data leakage in the first place. First of all, be suspicious. Data leakage can happen to everyone in a million different ways. My best advice is to always think about it and suspect every result you get. Domain knowledge is critical here. You need to have a full understanding of your problem domain in order to say that something doesn't make sense and need further investigation, like I did a few times in the examples. Plan your evaluation. You need to start your project by thinking about how will you evaluate the model. How can the production data be different from your research data? Do I have groups like in the second example? Do I have time series like the first example? Maybe I will have new categories and many more of these questions. Code reviews. So I really like code reviews, maybe the only one in the world. Take a coworker data scientist and just explaining your method. What features you extract, how do you evaluate, what preprocessing do you do, and hopefully you will find some problems or at least point you to some potential pitfalls. Work iteratively. I know that you all want to try the new deep CNN RNN with residual transformer attention of guns with some cyber blockchain layers of buzzwords. But it's not a good way to start a project. Starting with a simple model with a small number of features and making it more and more complex iteratively gives you full power on your research. And if you see something that doesn't make sense, you can easily come back to the version that it was added and find your problem. And finally, in the words of Joseph Heller from Catch-22, just because you're paranoid doesn't mean they aren't after you. Hope I made you all a little more paranoid. Thank you very much.
Hi guys, I'm Alex. I'm here to talk about the multi-label classification. Sorry. So a few words about me. I'm a developer and/or data scientist at Twiggle. These are my contacts. What I want to do today is to explain a bit about multi-label classification, what it is, and then show some techniques and methods how to access and solve these problems using some code, but not a lot of code, so don't be afraid. Okay, so before talking about the multi-label classification, let's talk about regular classification. I'm sure most of you are familiar with it, but yet I want to make clear. So regular classification, we want to understand an object and tag it to a binary answer. So for example, hot dog or not hot dog, this is of the art regular binary classification. And multi-label classification is not much bigger problem of that, but it's like a bit difficult. So in here, we don't want to label it into a binary yes or no answer, but into binary vector. For example, in this picture, we can see there is a house and a grass and a flag and a sky. So instead of asking, is there a house in this picture or is there a grass, we want to ask one question and label all these answers. So basically, the input is some data, and the output is a binary vector of yes or no. So who needs it? So actually, anyone who does regular binary classification will probably need multi-label classification at some time, as in image categorization, as I showed earlier, in text categorization, if you want to classify text into a subset of categories in medicine, bioinformatics, and all kinds of stuff. So before I show some techniques, I want to get something straight. Multi-label versus multi-class, which sometimes get confused. When we're talking about multi-class, it's a regular classification, but it's not binary, meaning the rating system here in Lubovsky can be G or PG-13 or R-rated, so it can get several different values, and the gender is a subset of all the gender it could be. So this is multi-label. So this is clear. Okay, now to the code. So there's a bunch of stuff here, how to generate the data and the sources and some explanation. I will not go over this. You can check it after your talk. So how do you approach by a multi-label classification problem? The first technique is the transformation methods, which is actually to take the multi-label and turn it into single-label binary problem, which we know pretty well how to solve. So the binary relevance does exactly this. So suppose we have a problem, we have a data which is X, and we want to label it into several labels, Y1 till Y4. So we can take our favorite single label classification algorithm and run it 4 times on the data and get 4 answers, and then merge them all together. So this will work, but it takes some time, and if there are any connection between the labels, it will not get it. So in order to get the connections, we can use something called classifier chains, which is it's also iterative and works basically, it works pretty much the same. We have the same data. We run it on the first classifier. We get the answer for Y1. And then we get the output for Y1, add it to our data, and run it on Y2, and so on. So this sounds pretty weird if you see it on first time, but actually it does make sense. I can show you using example. I hope everyone can see it. So basically here we want to label some movie into a subset of categories. So first we ask if the movie is a romance or non-romance, and we get an answer that's not. That it is. Then we add the romance into the movie data and ask if it's horror or not horror, and we get it's not. So why does it make sense? Because if we look at the movie genres in a graph, the romance and the horror are pretty far away, pretty far apart from each other. So when we get an answer for something that it is romance, it takes the answer more to the romance part and not to the horror. So basically, this is kind of the intuition behind the stuff. But it also takes a number of iteration as the number of our labels. The third and the last technique of turning this data into a single label question is not to look at the labels as columns, but rather as rows. So we can name the first row as 1, and the second one as 2, and the third one is 3. And then we can see that we get 1 again, and 4 and 3. So we took our multi-label classification problem and we turned it into a single label, but with multiple values, which is much easier to solve. And we have a number of known algorithms for that. So it works fine on some set of problems, but if you have a very large subset of labels and they are different from one another, you can have a lot of different values, which might be difficult to solve. Sorry. So the next technique is adapted algorithm. As you know, we have multiple algorithms for multi-label classification, for single-label classification, like k-nearest neighbors, decision trees, some boosting, neural networks, and all kinds of stuff. And some very smart people at universities thought of it and adapted it into multi-label problems. So for example, I have as an example multi-label KNN. I'm sure you're familiar with the KNN algorithm. I'm not going to explain about the multi-label KNN because I don't fully understand it. It's pretty hard. But here I have a link for the original article, and you can check it for yourself. The problem with this algorithm is that we don't have too much adaptive algorithms. I mean, not every single label algorithm was adapted into multi-labels. So, but if you have an algorithm that you want to use and it has a multi-label version, so. And the last technique is ensemble learning. I think in machine learning, in clustering, and in every machine learning problem, the more classifiers you run or the more algorithms you run is better. So basically what ensemble learning means is that you take your data, then you have some random subset of your data, run it multiple times on various algorithms, and then get multiple results, merge them, and you get your answer. So here ensemble learning works the same, but instead it not only subsets the input data, but also the output, the labels. So you have for each run, you have a subset of the input data, you have a subset of the labels, and then you run some of the previous techniques that I showed. You run it multiple times until you're satisfied. You merge the results and you have some answer. This answer is not so good, but this was all run on random data, so it's just to show how to run this algorithm. It's not real data. And that's it. Thank you.
Hi, I'm Lior. I'm an independent researcher, and today I'll speak about hypernetworks, which is a new idea in deep learning. And basically, a hypernetwork is just a neural network whose task is to generate weights for another given neural network. So I call this given neural network, I call it the target network, and our hypernetwork will generate weights for the target network. And some of the applications of this idea are, first of all, one hypernetwork could be used to generate a lot of different weight vectors for the same target network. And combining all these different weight vectors, you could get an ensemble and improve your prediction accuracy. Another application of hypernetworks is in the context of reinforcement learning. So if, for example, you have an agent which you want to train by competing against itself, then a hypernetwork can be used to generate, instead of this one agent competing against itself, you can generate a lot of different agents, and then your agents will be able to generalize better. So I'll just say a few words about generative methods in general. So I'm talking about methods like GANs or variational autoencoders. And for our purposes, I don't really care how you train a GAN, for example. I just care how you operate a trained GAN. So if you have a trained GAN generator, for example, all it is it's just a neural network. And to operate it, you need to sample a random vector, Z, feed the vector into your neural network, and then you get at the output, for example, an image. And the idea here is that if you take different vectors in the input, you get different images at the output. So your generator has the capacity to generate different images, of diversity of images. And I was curious about the question, which other things we can generate with a generator besides images and text and these familiar examples. And I asked myself whether we could actually generate weights for a neural network using a generator. And okay, I'm sorry, the slides are corrupted for some reason. So a hypernetwork is exactly what I described. It's just a generator that whose task is to generate weights for a given neural network. And you operate a train hypernetwork just like you operated just like I described before. You feed a random vector Z in the input, and you get at the output vector of weights for your neural net. The important thing here is that the weight vector that you get at the output, if you use it in your target network, then it gives you good results. So, for example, if our target network is a classifier, and you use the weights that you generated with your hypernetwork, then your classifier will classify correctly, at least most of the time. Questions at the end, I think? Oh, okay.
You mean final weights of the or initial weights of the network?
Oh, yeah, no, I'm talking, I want my generator to be able to generate weights, final weights, so that if I use them in my target network, I don't need to train anymore. I have weights which work well. Okay. Okay, so using the procedure of GANs, for example, to train a hypernetwork won't work here because a GAN requires a data set. And in our case, we don't usually have a data set of weight vectors. So we need something else here. Actually, training this is relatively simple. The concept is simple. All you need to do is just combine your hypernetwork with your target network into one big combined network. Treat it as one network and just use standard backpropagation. So our target network, which has some, it needs to solve some task, for example, classification, and it comes with a given loss function. And whereas in standard training of a network, we just backpropagate using this loss function and update the weights of our network. In our case, we continue the backpropagation and update the weights of the hypernetwork instead of the target network. And that's how we get a trained hypernetwork. Now, if I train, like I just explained, I run into a problem, which is that the hypernetwork learns to ignore the input and always generate the same output. And I'm not interested in that because I lose the ability to generate a lot of different weight vectors using my hypernetwork. So to solve this problem, what we need to do is add another term to our loss function. So it won't be only the classification loss that we have. We also add a diversity term. The diversity will encourage diversity, and the one example for a diversity term that we can use is entropy. So the larger the entropy of the generated weights, then the more diverse, the more different they are from each other. And I have this parameter lambda, which can balance between these two terms, because there's a trade-off between them. So a few words about the architecture of Hypernetwork. So the output of the Hypernetwork is a weight vector, and a weight vector could be very large. It could be tens of thousands or millions of dimensions, because that's the size of our target networks typically. And we don't want our hypernetwork size to explode. So we somehow need to restrict its size. And one way of doing this is by weight sharing. So the idea is you take your random vector Z, you use this block to transform it into a lot of small vectors. And each one of these small vectors is just one compressed representation of a filter in the target network. And so you have a lot of weight vectors, and you have a lot of little vectors. Now you want to convert each one of these little vectors into the actual weights of the filter. And to do this, you use a block, which is just a little neural net. And the idea here is to reuse the same block for transforming each one of these little vectors into the weights of a filter. And by using the same block with the actual same weights, you get weight sharing, and you can keep your hypernetwork small enough and more scalable. So I tried these ideas on an example of MNIST. MNIST is the data set of images of handwritten digits. And for the target network, I took a convolutional network with 4 layers. And I trained a hypernetwork, and I wanted to see 2 things. I wanted to see my accuracy, and I wanted to see the diversity. So for the accuracy, it's a simple thing to measure, because I could just generate a lot of different weights using my hypernetwork and measure the prediction accuracy of each one of these weight vectors and plot a histogram, for example. And my results were satisfying, because I got that all the weight vectors that I generated obtained high accuracy. But now I need to make sure that I also have diversity. In other words, I need to make sure that these weight vectors are different from each other, and they're not actually all the same weight vector. So it's not as straightforward to measure diversity, but there are a few ways. And the first thing we could do is form an ensemble. If you form an ensemble using all your weight vectors, you could see whether your prediction accuracy improves with the ensemble compared to the single weight vectors. And if it improves, it means that the weight vectors are sufficiently different from each other so that the variance of their prediction decreases. And indeed, that's what I saw. So that was a good indication that I have diversity. Another thing is, using the ensemble, I got better immunity to adversarial examples, which also indicates that there's diversity here. And one last thing, to probe this space of weights which I can generate, I could use PCA, principal component analysis. I can generate a lot of weight vectors, and each weight vector is a very high dimensional vector. But I can plot these high dimensional points in the first principal components. So this is what you see here. You see here scatter plots of principal component 1 versus PC2 and PC1 versus PC3 and so on. You see a few combination of plots here. And the interesting thing I think here is that we don't get like a simple Gaussian blob, which is what you would expect if you didn't have diversity, because in that case you only generate one weight vector and some Gaussian noise around it. But you actually get all these cryptic shapes and structures, and it's hard to interpret them, but they're definitely curved and nonlinear, and I think that's another indication that of diversity. And that's all. Yeah. So the question was the relationship between the size of the target network and hypernetwork. So in my case, the hypernetwork was about 30 times as big as the target network. But if you try to count how many different weight vectors that my hypernetwork can actually generate, so it's hard to count, but effectively, I think I managed to generate much more than 30 different weight vectors. So
that were good weight vectors?
Yeah, that were good weight vectors. So that means that my hypernetwork actually learned some relationship more than just memorized 30 different weight vectors. Yeah.
Yes. This setting only generates weights, but the architecture is always the same.
The architecture of the hypernetwork? The target. Yes. Okay. Yeah. This idea here only generates weights for a given fixed architecture. There are ideas of how to generalize this for generating various topologies or architectures, but I think that's more complicated. Yes. Okay. So the question was, how does this work compared to Bayesian deep networks? So I did some comparison. I mean, there are a lot of methods of Bayesian deep networks. So I took just one which was easy for me to reproduce. And I mean, I get comparable results, first of all. Depending on its aspects, in some aspects I get better results. Some aspects they get better results. But this can also be seen. It can also be seen as a Bayesian, framework. I think. Well, it's a bit philosophical, but I think the Bayesian framework has a lot of flaws in it. But basically, this is also. It can also be seen as a Bayesian idea. Yeah. Okay. Thanks.